Okay, so the basic algorithm for shortest path now follows these two ideas of this refinement with BFS and the continuous Dijkstra. The idea is that we have the source vertex, and let's assume that we already know the group of I-1 closest vertices. Those are I-1 closest vertices. And like in the idea of this flooding, this group X, you can think about it once we decided that we know the distance to a vertex, its distance is fixed, it's joined this occupied set, and it's out of the game, right? So now the question is, of course, to find the next vertex, the vertex that is the ith closest among all the vertices in the graph to the source vertex S, right? And the question is how to do that. So the basic strategy would be to repeatedly do the following. So let me first describe the meta algorithm, and then we will go again into how to do it. So initially X, the set of vertices we know the distance to, include only the source. And now X is going to be containing the I-1 closest vertices to S. That is going to be the invariant. Now, among all the nodes that are outside X, right, the complement, we are going to find the node that has the best distance if it comes from a vertex of X, right? So the idea is that the ith vertex must come, the shortest path for this, the ith vertex must come to a vertex of X. So we just need to compute this distance of every vertex V where you arrive to be to an edge from X, and that gives us a candidate distance. So we compute for all the edges in the complement this candidate distance, and we take the one that achieves the minimum. That's the closest one, and this would be the ith closest vertex. We update the distance to this vertex, we add this vertex to the occupied set, and we move on to the next vertex. And I don't know why this happened. And of course, the question is how do we implement the details exactly, right? So what do we know about the ith closest vertex? This vertex that is outside X, right? So X contains the I-1 closest to S. And now we have the vertex V, which is just outside, right? And the claim is, so let's assume this is S, right? Now think about the path from S to V. The claim is that the path must look like this. It arrives to a vertex and then it jumps with a single edge to V, right? So the claim is this is the situation. Importantly, this path P is included inside X. It doesn't go out. So to see why this is the situation, let's assume that this is, of course, false, right? That would be the most natural approach to do it. So, okay. So if it's false, right, then the set, this will be the set X, but the path now is going to do bizarre things, right? So the path might go out, visit some vertex Z, let's say, then maybe come back in and then go to V. That's one possibility. That's not the only possibility, right? But if this is true, notice that the distance of Z is smaller than the distance of V. The distance from S to Z is smaller than the distance from S to V, which means that Z is closer than V to S because P is the shortest path, and we had the hereditary property, so this is indeed the shortest path to Z, but that's a contradiction. That means that Z would be the ith closest vertex to S and not V as we assumed. So that's this proof of this claim. Okay. So let's see an example of this basic algorithm. So in the beginning, In this graph, we just know the start vertex A and the distance is 0. Now we inspect all the outgoing, all the vertices outside, but we really have to inspect only the vertices that have an edge to the occupied set. So those are only those vertices, this one, and this one. This is 13, this is going to be 6, this is going to be 9. So this is going to be the next vertex, right? Okay. So vertex C indeed is going to be distance 6, and now those vertices A and C are occupied. Again, we repeat this argument, right? So this is candidate distance 9, this is 24, this is 36, this is 14 from this, but it's 13 from this. So write 13. And now the cheapest one is this, 9, right? So next we handle B. And now we continue in this fashion, right? For every after we updated the distance to a vertex, we check all the other vertices if they have a path coming from the occupied vertices, and we see if their distance is updated, right? And we continue in this fashion until we occupied everything. And that's the basic algorithm. And right, and essentially what we already proved was that the ith closest node to the source is adjacent to the set X, which implies the correctness. But the question, of course, is how do we do this process of finding it? And the way I described it currently was that we have the set X, we have the complement set, V minus X, and I looked on all the edges that are crossing from X to Vx, right? So this is called the cut. So this is one way to do it. Of course, that's not going to be very efficient. There are better ways to do it. Okay, so what do we have so far? We proved that the basic algorithm is correct, kind of, because we didn't really describe the details. So the question is what are the details? And of course, how to implement it efficiently. And that's what we will tackle next.